Can you hear me? Okay, I think it is good. So we will try to complete this today. So I think it's from operating system 3 easy pieces. So we will try to do it by today and complete it. And minimum I think 50 pages we will try to do it. Um, I would assume like it would be a I think 1 hour or 1 hour 20 minutes I think it would take. So let's start. So the the part which we are starting is from the chapter 10, which is multiprocessor scheduling in advance. So you should have bit of knowledge about the congruency, and I will start from here due to that. So I think it is over here. Yeah. So we will try to complete it by today. Okay. So this chat will be introduce the basics of multiprocessor scheduling as the topic is relatively advanced. It may be best to cover it after you have studied the topic of concurrency in some detail. That is the second major easy piece of the textbook. After years of existence only in the high end of the computing spectrum, multiprocessor systems are increasingly commonplace and have found their way into the desktop machine, laptops, and even mobile devices. The rise of multi-core processor in some in which multiple CPU cores are packed onto a single chip is the source of this prolifer proliferation, and these chips have become popular as computer architects had a, have had a time making a single CPU much faster without using way too much power, and thus we now have a few CPU available to us, which is a good thing, of course. So the first is basically we what is like these kind of multi-processing system is increasing in laptops and all that, and the rise of multi-core processor, and we just using different like CPU cores to do different tasks, and we might want to like use a single CPU before like these multi-core processing units. We just use one CPU for all of the tasks, and that's fine. Just written here like making a single CPU much faster without using way too much power, and thus we now have few CPUs available to us, which is a good thing. So there are difficulties that arise with the arrival of more than a single CPU. A primary one is that the typical application, like some C program you wrote, only uses a single CPU. Adding more CPU does not have to rewrite your application to run in parallel, perhaps using threads. So, like one of the difficulty, like we can say that there is this difficulty. You can say this that arrival of more than single CPU, it is not a primary reason why it doesn't run in parallel. So, like the remedy is that you have to rewrite your application to run in parallel. So there is only one solution is that. So we will rewrite our application to run in parallel and perhaps using thread. Uh, and multi-threaded application can spread work across multiple CPUs and thus run faster. Okay, so these we call as a multi-threaded applications, and we can see that um, advanced chapter required material from both sides of the book to truly understand while logically fitting into a section that is earlier than set a prerequisite area. For example, this chapter on multiprocessing scheduling makes much more sense if you have read the first piece of congruency. However, it logically fits into the part of the book on virtualization, generally and CPU scheduling specifically. Thus, it is recommended such chapter to cover out of the order, in this case after the second piece of. So we will cover it just now because I have some kind of uh, previous knowledge from before of this. So the next part is the single CPU with cache. So we can see that it is a single CPU and we have given a cache and a memory. So the cache and the memory will be interconnected by this time, and we can see that a single CPU with cache is nothing but a normal cache memory. So beyond application, a new problem that arises from the operating system term is not surprisingly that of multiprocessor scheduling. Thus far, we have discussed a number of principles behind a single processor. So one of the thing is that thus far we have discussed the number of principles behind single processor scheduling, how we can extend these ideas to work on a multiple processor, what new problems must we overcome, and thus our problems. So the 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 multi-processing like scheduling, what we have been given here is that uh, like the single processor, what we do kind of do in the single processor, so we wanted to do in multiprocessor. So what kind of scheduling we should do in that? So it is basically asking us to what we are actually going to be doing. So the single scheduler is for that single processor for that, but multi if we have multiple cores, so what kind of multiple scheduling processing algorithm or things we should do? So the first is the architecture of the multiprocessor we can understand. To understand the new issues surrounding multiprocessor, although there is one crux written here, to schedule jobs on multiple CPUs, how should a CPU schedule jobs on multiple? What new problems arises and do the same altogether? Basically, what I was saying that it is same as what I have written or what I have told you about that. It's like how we will use that kind of knowledge before we have done that, or there are different scheduling algorithms, and is it same as the multiprocessing unit also, and like the same algorithm works or not? To understand a new issue surrounding multiprocessing scheduling, we have to understand a new and fundamental difference between the single CPU hardware and multi CPU hardware. So understand the fundamentals. So single CPU and multi CPU hardware. So there are two types of hardware. One is single CPU and the another one is multiple CPU. So the different center around the use of hardware cache and the different centers around the use of hardware cache. So this is the figure which we are talking about. So this is for the single CPU, which we can see at the top here, and and exactly how data is shared across the multiple processors. We have now discussed this issue further at higher level. Details are available elsewhere, in particularly the upper level or perhaps graduate architecture course. In system with a single CPU, there are hierarchy of the hardware caches that is in general help the processor run program faster. So a system where there is only single system, CPU. the hierarchy of the hardware, caches that generally help the processor run faster, program faster. And caches are small and fast memory that in general hold copies of popular data that is found in the main memory of the system. Main memory, in contrast, holds all the data, but access to this larger memory is slower. So in a system with a single CPU, there is a hierarchy of hardware cache. So that in general helps the processor run faster. So we know about the hardware cache we have here, and the cache are small, fast, and generally. So we can see that so main memory, in contrast, holds all the data, and but accessing to it, the larger memory is much slower, and by keeping frequent access data in the cache, the system can make slow memory appears to be the faster. So we actually keep one of the things like we can see here is that in memory is like a used storage, like you keep all the things in the fridge, but you if you have to know to a like things that you want at any instance, so you should take it out and keep it on your stovetop, you can say. And like you don't want anything to when you're cooking, you don't want anything to be like what you required for cooking any kind of meat or any kind of thing. You don't want them to be in a fridge or like in a storage container. Regardless, you want them to be on your stove top or on your table top to be accessed easily and able to like give you access more frequently. So this is like for example salt or any kind of things you use on daily basis. So we might see other examples here also. So let's see. Okay. So the this is the two CPU with cache sharing system. So we will use a bus system. So there is a bus here. So we will use bus to share this cache over this line. It could be different kind of buses. So for as an example, consider a program that issue an explicit load instruction to fetch a memory from a value from memory, and simple system with only a single CPU. The CPU has small cache set 64 KB and large memory main memory. The first time a program issue this load, the data reside in the main memory and thus take a long time to fetch, perhaps in the tens of nanoseconds or even hundreds. So okay, so CPU has small cache, let's say 64 KB of data and the large memory. The first program issue this load, so whatever data or like program that they want, like the user, it is given to the CPU and the data reside in the main memory. So it's all in the main memory at currently, and this take a long time to fetch, perhaps in the tens of nanoseconds or even hundred. The processor anticipates that the data may be reused and puts a copy of the loaded data into the CPU cache. If the program later, if the program later fetches the same data item again, the CPU first check it for the cache. If it would find the data is fetched more quickly, say just to give you an answer, and the program just transfer. So from this part of the paragraph, we can understand like how actually we are going to make the program run faster. So it is like having a quick access to a things that is more frequent to occur in the program. So we store it in a cache, and cache has a notion of locality. So what is local to you? Like how much like nearby a a storage or a program unit you want to access. So we can see here is that this locality of which there are two kinds of locality. So the first is temporal locality and the second is spatial locality. The idea behind The idea behind the temporal locality is that when a piece of data is accessed, it is likely to be accessed again in the near future. So any kind of data we access, it is likely to be accessed again in near future, and is likely to be accessed again in the near future. And imagine variable or event loops themselves. So any kind of things that is likely to be accessed in the imagined variable, even instruction themselves being accessed over and over again in the loop. The idea behind spatial locality is that if a program accesses a data item at a address x, it is likely to access data item near x as well. Here, think of programs streaming through an array or instruction being executed one after the other, because locality of these types exist in many programs. Hardware system can make good guesses about what data to put in a cache in the software. Okay, so we can think here is that the idea behind the temporal locality is that when a piece of data, like any data we take, and it is likely to be processed again in the near future. Any data that is going to be processed again in the near future, like let's say a a variable we store currently, and it is surely going to be processed for like going to be accessed, or we require them in the near future again. So we just store it. So the idea here is that like like behind spatial locality uh, is like access to be over and over and over again, so it is called as temporal locality. So any kind of thing that you want to be like access again, it's a temporal lobe of your brain. So you want to access it again and again and again without trying to do a quick search from, or you have to grab it from your main storage system. So you will just access it again and again. So it's called temporal locality. Okay. So idea behind the spatial locality is that the program accesses data item at an address X. So we access the data at X. It is likely to access data items near X as well. Here, think of program streaming through an array or instruction being executed one after the other. Because locality of these exist in many program, hardware system can make good guesses about data to put in the cache and the server. Now for the tricky part, what will happen when you have multiple. So we can say for the spatial locality is that data item at an address streaming through an array or an instruction being executed one after another. So because locality of these type exists in many program, hardware system can make good guesses about which data to put in the cache and thus further. For the tricky part, what happens when you have multiple programs in a processor in a single system with a single main memory as well as figure 10.2. As it turns out, caching with multiple CPU is much more complicated. So, imagine, for example, that a program running on CPU 1 reads a data value with a data item with a value D at address A. Because the data is not in the cache of CPU 1, the system fetches it from the main memory and gets the value D. The program then modifies the value of the address A, just updating its cache with the new value D dash, writing the data through all the way to the main memory. So the system will usually do that later. Then assume the OS decided to stop running the program and move it to the CPU2. Thus the program then reads the value at the address A, and there is no such data in CPU2 cache, and thus the system fetches the value from the main memory and gets the old value of D instead of the correct value D dash. Oops, this general problem is called the cache coherence. So this is the general problem, like what we actually call it as a cache coherence problem. So uh, like any kind of access you want to do or any kind of things, any kind of like things you can do uh, with like you have to do it in a such a way like there are certain kind of locks or any kind of things whatever like mutex or that to avoid this and get consistent data over everything in your system. But at current point we may see that like these kind of things are like problem in this multi-processing thing. So we can read it again like turn on the caching with the multiple CPU is much more complicated. Imagine for example that a program running on CPU1 reads data item from D like D this was that D was written there and we have read that and because the data is not the cache on the CPU on the system for written to trucks and the system says okay do it right trust. So after the system is structured, uh, it can okay. So okay. So program modifies the value at address A, just updating the cache of the value. So it's just simple as that. It just changes the value at some point, and it is called as cache coherence, and we are accessing the old data. And there is a vast research literature. There are many studies on this. Here, computer science class or three to make more to task basis. So the base the vast research literature is called make some major point in computer. So the basic solution is provided by the hardware for monitoring.